And we are going to get started with something that I remembered that you need for the homework that is due Friday that frequently confuses people, the potentiometer. Okay, this little blue rectangle thingy in your kit with a knob on it and 3 pins. It is not necessarily immediately obvious how these pins are connected or what the corresponding circuit diagram is, so I'm going to make sure I cover that briefly to make sure people are not confused about how to plug it in to your breadboard before we move on and talk more about op amps today. So, zooming back out, you will see a circuit symbol that looks like this. It's a resistor with an arrow going to the middle of it, right? And this represents an adjustable 3-terminal potentiometer. Okay, so what that does is we've seen a voltage divider before with 2 fixed resistors, right? Where we have V in, V out, and then R1 and R2. What this is doing is just letting you slide that middle contact to change R1 and R2 so you can change V out. Okay, so as if you, for example, connect this to 5 volts on one end and 0 volts on the other end, and as you slide, when I say slide, and you turn this knob all the way from one end to the other end, then the output is going to change all the way from 0 volts all the way up to 5 volts. The important part here is that if you look at this thing from the top, it has 3 pins like this. Okay, so they're offset from each other. When you put that in the breadboard, it is important to make sure each pin goes in its own row. Okay, each pin in its own row, like this, and that way, remember how a breadboard works, each pin is electrically isolated from the other. So those 3 pins, the 2 outer pins, correspond to the kind of 2 outer terminals. So the resistance between those, the resistance of the whole thing is always fixed. This middle pin is the adjustable one. Okay, so if, as some students sometimes make this mistake, you rotate this thing 90 degrees and put it in the breadboard like that, right? Then the 2 outer pins are shorted to each other because they're in the same breadboard row, so don't do that. Okay, just make sure you look at this thing again. It can be a little hard to see sometimes, but if I zoom in, you can see how, again, these 3 like that would fit in each row of the breadboard. If I rotate it 90 degrees like that, then these 2 are going to be in the same row and they're going to short. Okay, so that's just kind of a common mistake when people are using a potentiometer for the first time. This is something that, anytime you turn again, this is making me feel old thinking about radios, but you said last time most of you grew up, you did have radios and not just Spotify, like the volume dial on a radio, right? Or any dimmer switch for, not so much for LEDs, it's a little more complicated, but for incandescent light bulbs, that sort of thing. This is just a potentiometer, a variable resistor, okay? So that is not the point of homework 3, but you are going to be using one along with op amps in homework 3. Okay, so any quick questions about the potentiometer? Yes? So V out is the middle? Yes, V out is, so I wrote adjust here, sorry, but that should just be, the middle pin is V out. Or adjust for adjustable, whatever you want to call it. Okay, switching gears back to op amps. I know we had the guest lecture on Friday, so you're going to have to jar your memory from last Wednesday. I want to get through a lot today, so you have everything you need for the homework before we move on to the next topic. So I'm not going to review all the assumptions and everything that you should have written down in your notes from last time, but we'll kind of remind you about them as we go through. Yes?
I was just curious, what was the sketch leftmost? What was that indicating again?
Over here?
Yes.
That is the circuit diagram symbol you'll see for a potentiometer. So sorry, it got messy with all the annotations there. The pure symbol on its own, like this, is a resistor with an arrow pointing to it, indicating. So the 3 terminals would be 1, 2, 3, corresponding to, if you look at the bottom of the physical potentiometer, 1, 2, 3, like that.
Thank you.
Yep. Okay. Switching gears back to op amps. I'm going to draw a line here. Last time at the very end of class, we squeezed in the inverting amplifier. So an op amp that puts a minus sign on a voltage but can also amplify it. by choice of resistors. So to kind of jar your memories about how op-amp math works, I'm going to ask you guys to work through a similar example for a slightly different circuit. So we have our op-amp. Our op-amp has an output voltage. We are going to have an input voltage. I'm going to call it Vin this time because I was lazy about subscripts. Calling it Vs last time caused some confusion about power supply voltages, which again, I'm not going to draw. It's just implied that those are there. We have a source resistor Rs that is going to go to ground this time, and a feedback resistor Rf that is going to connect over to Vout, and we're going to have a load resistor to ground, RL. So the question for the poll everywhere I'm going to launch in a second is going to be, what is Vout for this circuit? But remember some of the ideal op-amp assumptions we can make. I have negative feedback, okay, so my output is connected back to my inverting terminal, which I should have drawn connected all the way there. So since we know that is true, we know that the voltages at the two inputs have to be equal, right? So here I'm going to have Vn, and at this node there, I'm also going to have Vn. And I also know that the currents into the inputs are 0. So remember last time, again, we kind of did this in a hurry at the end, but I can apply KCL to that node. So summing currents going into or out of the node, but I know one of them is 0. And it will also help if you mark and follow sign conventions on your two resistors. You don't have to do it the way I just did, but as long as you're consistent with wherever you do it, you can define it the other way. Given all of that set up, what is the equation for Vout? I'm going to launch the poll everywhere and give you guys a few minutes to work on that. And it might help to, if you do not remember all what we did on Wednesday, look back at what we did at the end of class on Wednesday for the inverting amplifier. And you should be able to follow a very similar procedure here. And I just realized I didn't actually write the word potentiometer down here anywhere, so for people looking at the lecture notes in the future, potentiometer, I in there. Okay. Oh, sorry, and the poll everywhere I have it is just R. Sorry, ignore that subscript S there. Sorry about that. This should just be an R. So we have RF and R because this R is not connected to the input or source voltage, so it's just an R and not an RS. Sorry about that. Thank you for catching that. Providing a hint to help you along. You define a current there and a current there through each of those two resistors. Remember that applying KCL at this node, if you know the third current into this input is 0, those two currents have to be equal, and you can always apply Ohm's law to a resistor. And so we're not quite at all the responses yet, but maybe a little hint to boost you along if you were stuck.
Oh,
Okay, we're around 95 responses, so I'm going to give this maybe another 30 seconds, and I'm going to close it. Okay, 15, 10, 5, 4, 3, 2, 1, deactivate. And the correct response, which only about a third of you got, so clearly I need to do a better job of swinging op amps, is A. Okay, so let's, rather than jumping right to that equation, let me take this a little slower and see if I can explain how we get to that equation. Okay, one thing at a time. Shading the light there. Ideal op amp assumptions. I have negative feedback, and so I know these two voltages have to be equal. Okay? I know this one is Vn, therefore I know this voltage on that input also has to be Vn. Does everybody believe me so far? Okay. Drawing that node a little bigger. It's kind of crowded over there. I know that this current equals 0. So this is just redrawing this node because this part of the drawing got too crowded, okay? And then I know that this current, call it I1, has to equal this current I2, right? That's just summing the currents into and out of that node. And so I know I1 must equal I2. Everybody believe me for that part? And if you don't believe me, you gotta speak now or forever hold your peace, because then the rest of it's not gonna make sense.
Sorry, how do you know the direction of current?
You don't know the direction of current. That is the direction that I define based on the passive sign convention I defined for the resistors. So positive current into the positive terminal of resistor, but remember that is just a mathematical convention. Physical resistors do not have polarity. A couple people have been confused about that so far. So if I had, so you get to pick which way you assign the passive sign convention, just like you can pick which way your positive x-axis is in a mechanics problem, right? If I had gone like this, then I would also just know that, say if I call that I1 and I2, I1 equals I2. If I had done this, well then I know it's impossible to have two positive currents flowing into that node, right? So here I would have to get I1 equals negative I2. The way I've defined the sign conventions there, one of those currents would have to be negative. So all three of these are a valid way to write the sign conventions down. It's just if I do it like this, and again, since I know that one equals 0, then I know that one of these would have to be negative. That answer your question? Okay. Okay, so assuming I did it like this, I know those two currents are equal. I'm now going to apply Ohm's law to each resistor one at a time. Right? So for this resistor here, just resistor R, okay, I know V equals IR. The voltage drop over this resistor, as I have defined the sign convention, it's Vn on one side, it's 0 on the other side. So positive side minus the low side, Vn minus 0 is just Vn, right? So that's Vn minus 0 equals the current I times R. I'm going to do the same thing for the other resistor, okay, for my RF. Okay, voltage drop over that resistor. Again, voltage drop over this resistor, not the voltage relative to ground. Notice how this resistor is not connected to ground. Okay, voltage drop over that resistor, positive side minus the negative side is V out minus V in. Okay, everybody believe me on that. Okay, it's not just V out, it's not just V in, it's not negative V in, it is V out minus V in, the voltage drop over that resistor. N equals I times RF. Okay? I know, again, because of this, those two currents are equal, so I can rearrange and set those equal to each other. Right? So I have I equals V in over R for this one, and for this one I have I equals V out minus V in over RF. Everybody believe me for that step? In the back.
If we had a different coordinate system, like if we had VA minus V out for RF and VA minus 0 for R, would we achieve the same result?
So but you're asking if you would get the same result if you did a different sign convention for the currents? I didn't totally hear the beginning of your question.
Yeah, like if like the differences would flip, like it would.
Yeah, because then you should have two minus signs, which will then cancel out in the final equation.
Okay.
Okay, so I'm going to set, and which I think should hopefully will be clear in the next step. So I know these currents are equal. I'm going to set those equal to each other. Right, V in over R equals V out minus V in over RF. So I think if you did what you had asked, you would have a negative sign on each side of this, and then they would just cancel out, and you would still have the same equation.
Yeah.
Okay. So we can write that as V out over RF minus V in over RF equals V in over R. We want to solve for V out. So rearrange the whole thing, and you get V out equals 1 plus RF over R times Vs. So now we've gotten rid of the negative sign. We're not inverting it. Okay, this is called a non-inverting amplifier. So very similar to an inverting amplifier, but kind of where we've connected the resistors and the input voltage is different. And I don't have the page open in front of me, but if you go back to the notes from last time, you can compare it to that and kind of see how the configuration is different. The difference here being that technically with the inverting amplifier, you could make the output less than the input by choosing the resistors. Here we have this 1 plus something, so you can only increase the output here. Even if RF is 0, the lowest this quantity in parentheses can ever be is 1. Okay, again, even if you didn't totally follow that derivation, at the end of the day, the point is you're going to have this library of op-amp circuits in your notes, right? So you go look up non-inverting amplifier, there's the equation for non-inverting amplifier. If you already have inverting amplifier, you have the equation for inverting amplifier. Yes?
How is it different from an inverting amplifier?
How is it? So this one, there is no negative sign in the output. So in an inverting amplifier, there was a minus sign.
But in terms of like the circuit diagrams?
You'd have to go back through the notes and look at the diagram from last time. I don't have it in front of me, but I don't have it memorized, but the way the resistors and the source are connected is different. Yes?
So does inverting versus non-inverting just imply that the output is negative versus positive, like in terms of the voltage?
Yes. But the question was, does inverting versus non-inverting imply the output is negative or not in terms of the voltage? Yes. Inverting amplifier, if the input voltage is positive for an inverting amplifier, the output will be negative and vice versa. For here, the output will have the same sign as the input. Okay. Other question in the back?
Yeah, I'm just still pretty confused about the purpose of the load resistor. What is it generally good for?
So the question was being confused about the purpose of the load resistor. The point of the load resistor is that it does not affect this. So even though if you remember way back to just a voltage divider, right, with two resistors, where we talked about how if you connect a multimeter here, in reality that's like putting a very large resistance in parallel, and that's going to affect the output, right? So the V out, if I have R1, R2, and RL here, if I solve this circuit for V out, it depends on RL. V out there is a function of all three R2, all three resistor values. With the op-amp, adding a load resistor does not affect the output. Yeah, so we could do this entire, like, pretend that's not there, right? We could have just done this entire analysis and gotten the same answer. If I add a load resistor, like a measurement device, a multimeter, and oscilloscope, it's not going to affect the output. Because remember, the op-amp has that external power supply, which we usually don't draw because it also doesn't really come into the math, but the op-amp can provide extra power to kind of prevent the output from sagging like you would have in this case. Does that make sense?
Yeah, so basically, if you're building like a real circuit of non-inverting amplifier, would you even need a load resistor?
Well, no, so the load, don't think of the load resistor as literally putting a resistor there. Think of it as the measurement equipment.
Okay.
Okay, so again, think the op-amp is usually going to be, last time I think we talked about strain gauges and EKG, things where this VN is coming from some sensor, right? It's not just like a magical VN. Here it's just kind of a VN, it's just a magical mathematical quantity I'm applying, right? In reality, that is going to be coming from some sensor that is not really capable of providing a lot of current on its own, right? Or if you hook up some measurement equipment, again, a multimeter siphons off a little bit of current, right? And that's going to affect the reading. So you remember one of the very first op-amp circuits we saw was just a buffer, right? There weren't even any resistors there, it was just a voltage follower. It protects the sensor from whatever's measuring it or drawing current from it to kind of help prevent, I can't think of a great mechanical analogy for this, but just kind of help prevent the voltage on whatever you're measuring from sagging and being affected by the measurement equipment. So that the kind of point of drawing this here, we've gone through it a couple times now, but you go through the analysis, it's like, oh, hey, it doesn't actually depend on RL, and that's the point. Okay? Yes?
Sorry, I didn't catch what's the non-inverting referring to.
Non-inverting mean that, pen is covering it up. There is no minus sign on this, so it is not inverting the input. Whereas if you go back to the notes for the inverting amplifier, there is a minus sign on the output. So it is inverting or making the output negative when the input is positive.
So that will be just to like add a negative sign on the right hand side?
The equation was not exactly the same. Let me flip back. So you should have this in your notes from last time. There wasn't the 1 plus part. It's just negative RF over RS. But the point, the naming convention comes from the presence of this minus sign out front, inverting and non-inverting. Okay? All right, other questions on the non-inverting amplifier? Yes?
Basically, if the input goes into the negative terminal, like VN or VS goes into the negative one, it's inverting that.
Not, well, so the question was if the input goes into the negative terminal, it's an inverting amplifier. That, but then the positive terminal is also grounded. So it's not just, it's moving this, it's basically swapping the VN and the ground here. Yes, I needed to double check. I guess the resistors are actually in the same place. The resistors, they're going to be, other circuits we'll see where the resistors can get shuffled around, but yes, that's another way to think of it. Switching the VS and the ground from this diagram to this diagram gives you inverting or non-inverting. Okay? All right. Other non-inverting amplifier questions? Yes?
In your equation for V out, you have VS. Is this?
Oh, sorry, that should be VN. That's me being terrible with subscripts again. And I don't know if you backtrack through, okay, VN. Okay, yeah, I think I was consistent with the VN through the rest of the work. That should have been a VN. Thank you. Okay. Other non-inverting amplifier questions? Cool. What happens if we make life worse and throw capacitors in there? Let's find out. So, we are going, instead of a resistor in one of those places, we got our op amp. I should probably learn to draw these bigger to make this easier, but I'm not. We're going to ground the non-inverting input. We're going to put a capacitor, CS, or source, on our inverting input. I'm going to go to VN. this is going to be in. CS, we're going to have a feedback resistor RF. V out over here. Again, we are going to have that load resistor, which at this point you can probably expect isn't actually going to show up in the answer. Okay, again, we want to figure out what V out is. Remember, we still have Ohm's law that's going to apply to that resistor. We have the capacitor equation that's going to apply to the capacitor, C dV dt, where that V is the voltage drop over that capacitor, right? And we still know our ideal op-amp assumptions are true because we have negative feedback, so the voltage there, since that is tied to ground, is going to be 0 volts. Ideal op-amp assumption, the voltages at the inputs are equal. Voltage there is also going to be 0 volts. Ideal op-amp assumption, I drew this too small to draw it, but the currents into the inputs are 0. So kind of the same thing we knew about the currents for the previous problem. Okay, current through the capacitor has to equal the current through the resistor. Depending on how I'm going to draw the sign convention like this, plus minus, but you don't have to. Okay, given that setup, okay, ideal op-amp assumption, input voltages are both 0, input currents are 0, current through the capacitor has to equal the current through the resistor, and you know these equations. What is V out? Okay, I'm going to launch that one as pull everywhere again. What is the equation for V out? Providing a hint to move along because I want to get through as many more op-amp circuits as we can today. So looking at the capacitor, we have I equals CS, derivative of the voltage across the capacitor, which is Vn minus 0, so that's just going to be d Vn dt. Looking at Ohm's law for the resistor, the way I've defined the sign convention, I have 0 volts minus V out, so that's going to be 0 minus V out equals I RF. And as we've seen several times now, those two currents are equal. So I can solve for the currents and set them equal to each other. So if you haven't done that yet, try to skip ahead to that step. Solve for the currents in each of those two equations, set them equal to each other, and then get an equation for V out. Give it like another 30 seconds. 10. 5, 4, 3, 2, 1. Deactivate. Correct answer, which more of you got this time, okay, is B. So it looks like we were just having a little trouble remembering op amps from Wednesday, but after doing a few more examples, we're doing better here. So I'm not going to write out every single step, but set those currents equal to each other. Or, sorry, solve for the currents, rearrange, set the currents equal to each other, and you get V out equals negative RF CS D V in dt. So that is why this circuit is called a differentiator. It can take the derivative, granted with the minus sign, of the input voltage. Okay, so if, for example, your input voltage is, say, a triangle wave, like this, that's your input, then your output voltage is going to be the derivative of that graph. Okay, remember, think way back to high school calculus and just like sketching derivatives without worrying about the units on the y-axis here yet. The output is going to be the negative of that derivative, right? So here we have a positive slope, so the output is going to be a negative constant. Let me switch to a negative slope, so the output is going to be a positive constant, and so on. Okay, and the same thing for sine waves, parabolas, whatever function you can think of, this circuit will take the derivative of it. It's just also doing a negative sign. And you might ask, okay, cool, why would you want to do that? You can do something like totally analog PID control. Okay, so you all took system dynamics. We actually used to have an op-amp PID control lab in this class, but there's so much material crammed in that it's shifted over the years, so we don't do it anymore. So unfortunately for this one, you're just kind of seeing the theory and not actually getting to put it into practice. But we've already mentioned an inverting or non-inverting amplifier, right? So there's no calculus there. That's just multiplying it by some constant. So that's the proportional part of PID control. Here we have a differentiator. You can probably guess what's coming next. You can also have an integrator, but for the sake of time, I'm not going to make you guys solve this one. I'm just going to write it down. Oh, sorry, I should have paused there. Any questions on the differentiator first? Yes?
This is not like specific to the differentiator one, but why? Like, is the RF, it's not part of the actual op-amp, right? So
No, so everything drawn around the op-amp is external. The only op-amp itself is the triangle. Everything else is a separate part.
So, like, what would its purpose be? Or is it just like a component?
The RF, it is providing negative feedback from the output to the inverting input. So remember, one of the very first op-amp circuits we saw, just the voltage follower or buffer, there wasn't a resistor there, it was just a wire. You see the RF always comes into the final equation for choosing that scale factor, right? So I should have said the output is equal to the negative derivative of the input times a scale factor that I can choose based on the resistor and the capacitor. Just like for the non-inverting amplifier, right? The output is going to be some constant times the input. I can choose that constant by choice of these resistors. Same thing for the differentiator. Okay, I can choose if I want it to be 100 times the input or a tenth times the input or whatever. I choose the resistor and the capacitor to make that work. Yes?
This circuit kind of looks like a high-pass filter, so would it be affected by the frequency of the input?
We are going to get to that hopefully in the next 15 minutes. Short answer, kind of. Yeah, so this is assuming, not assuming that you're driving this with a sine wave, or a sine wave and changing the frequency, but kind of that. We might run out of time to do it today, but either at the very end of today or the very beginning of the next lecture, we're going to look at what happens if you analyze this with impedances and drive it with a variable frequency sine wave, and you can also build what's called an active high-pass or low-pass filter, similar to where we had just passive low-pass filter before, where the gain could never be more than 1. When you do it with an op-amp, you can get a gain more than 1. So sneak peek of where we're going, but I don't know if we're going to get there in the next 15 minutes. Okay. Again, for the sake of time, I am just going to write. I kind of hate just standing here and talking at you guys and writing equations down, but there are so many op-amp circuits that we don't really have time to do all of them as pull everywhere. So integrator is going to look pretty much the same as the differentiator, but with the capacitor and the resistor locations switched. So now we have the resistor RS over here, the capacitor CF up there. As usual, I'll draw the load resistor, but that's just kind of representing measurement equipment. It's not actually going to come into the math. You can do the analysis, and if you want to see the derivation, one of the videos in the lecture theory playlist actually walks through this. It's V out equals -1 over CS RF integral of V in dt. Okay, so this one is taking the integral of the input voltage. And again, if you combine an amplifier, an integrator, and a differentiator, you can do the math to do feedback control. And again, think of the gains you would want for a PID control circuit. You can kind of select the gain for each term by choice of the resistor and the capacitor. I see a hand way in the back corner. Yes?
Where's RF in the circuit?
Oh, sorry, I screwed up my subscripts. There is no RF. That should be CF and RS. I think I just got my subscripts. So honestly, since there's only one resistor and one capacitor, you don't even really need the subscripts here, but that should be CF and RS. So I drew the diagram correctly where the capacitor is the feedback element now and the resistor is connected to the source. So sorry, I think I will fix that in my notes too. CF and RS. Thank you for catching that. Okay. I think what I'm going to do, there are a couple other circuits I want to cram in here with the time we have left, and then we will do active filters at the very beginning of next class. So, the one we saw in the paper from Professor Shepard's lab last time, it's called a current to voltage converter. So here, if you have a current source, which again we haven't talked about really as much as we've talked about voltage sources, but something like a solar panel or a photodiode, which is kind of the opposite of an LED. Instead of converting current to light, it converts light to current. If you have a current source, IS connected to an op amp like this, so we got the non-inverting input connected to ground, feedback resistor RF, as usual we got the load resistor RL, so there, really simple equation, just V out equals I RF. Motivation for doing that being that things like a microcontroller like your Arduino cannot measure current directly. Okay, your multimeter can measure current. Microcontroller like an Arduino can only measure voltage. So in that paper they had this mechanical structure that was resulting in light being detected by a photodiode, which would generate a current, but they needed to measure that with an Arduino, right? So that was the little op-amp circuit. But if you remember the exact diagram I showed in that paper, it also had some capacitors in it because they were also filtering it in one step. So I forget exactly where this question was, but the question of like, can that also behave like a filter? Yes. Not in the example I drew right here, I didn't include a capacitor, but if you go back to the slides and look at the figure from that paper, there's also a capacitor in there. Okay, I'm going to slide that one up and get through a couple more, kind of get through as much of this as we can today, and then we'll pick up on Wednesday. Okay, next one is going to be differential amplifier. So I guess for the people who took the BME circuits class and built the EKG, you guys said you used an op-amp. Did you make a differential amplifier, or was it a different, which op-amp circuit did you use? Differential?
Yeah.
Okay. Okay, so differential amplifier useful if you need to amplify a really, really tiny difference between two voltages. Okay, so we are going to have, instead of tying one of the input, that line should have gone up to the, just pretend I drew that in the right place and it connects to the plus, you get the idea. Two inputs, V1 and V2, and we want to amplify the difference between them. Okay, so this time we are going to have matched pairs of resistors. So both of those have value R1. Both of these have value R2. V out is then R2 over R1 times V2 minus V1. So again, this difference can be really, really small, millivolts or microvolts or something. Again, thinking of putting electrodes on the human skin, right? Like the differences in voltage between just two places on the human body. But we can amplify that by choice of these resistors. So if R2 is a lot bigger than R1, then we're going to amplify that output a lot. And again, for each one of the things I have just shown, you can do the derivation. Okay, you can start with the ideal op-amp assumptions and apply Ohm's law and KCL to nodes and figure out the equation. But again, are you ever actually going to need to do that 10 years from now? Probably not, right? You're just going to have your library of op-amp circuits that you can go look up. And this is also not even an exhaustive list. The op-amps are kind of these nifty little things that let you do all these different things and operations on voltages. So we're kind of going over some of the key ones, but there are probably more than I could ever cover in multiple days of lecture here. So just the point is here, you kind of have these in your notes, or again, if you lose your notes, you can go look up. There's like a Wikipedia page with every op-amp circuit you can think of. You get the idea. Okay. After the differential amplifier, we're going to have a summing amplifier. So let me move this one over. Try and draw this. Give myself room so it doesn't get messy. We're going to have our single feedback resistor, RF. Positive input is going to be tied to ground. But now we are going to have as many resistors as we want. I'm only going to draw 3, but there could be more. So we have R1, R2, R3, V1, V2, V3. V out is going to be the sum. Little n equals 1 to big N of RF over Rn. Sorry, there should be a minus sign out front there. Vn. So it's letting you do kind of a weighted sum. So R1, R2, and R3 don't have to be equal. If you just want to add the voltages, then you do make them all equal, and then they're all going to have the same fraction. If you make all of the resistors equal, so each one of these R is equal to RF, then this fraction is just going to be 1, and the output will just be, again, it's going to be negative, but just adding the voltages. If you want to scale them differently for some reason, then you can pick different resistor values. Let me check how much time we have left. Okay, we have enough left, and I'm going to get started on the active filter thing because you need that for homework 3. But if you are getting a head start on homework 3 and we don't get far enough in the next 5 minutes, there is a video about this in the circuit theory playlist linked on Canvas if you want to kind of look ahead and see the derivation for both active, low, and high pass filters. But I realize I kind of went through a lot of that really quickly, so let me pause for 1 minute. Oh, darn it, I can't fit them all on the... People are kind of still copying these guys down. I know I kind of blasted through those because I wanted to get to all of them today. Any questions about current to voltage converter, differential amplifier, or summing amplifier? Yes?
Is like a key feature of the differential amplifier that the two resistances directly connected to V1 and V2 have to be the same? Like the R1,
Yeah,
R1
so
those always have to be the same for that equation?
Yeah, the question was, is it a kind of a key feature here that these resistances are the same? I would have to, so you could start with a general case here, like R1, R2, R3, and R4,
Yeah.
and chug through the analysis and wind up with some more complicated equation. So my guess is that if you then set them equal to each other, it reduces to this simpler form.
Okay.
So there would be some more complex equation with all 4 resistor values if they were different. I don't know what it is off the top of my head though. But yes, to get this kind of nice equation where it's just the difference multiplied by this single fraction, then these two need to be equal, and these two need to be equal. Okay. Yes?
And I randomly assign the, I don't know, like the positive and negative of resistance as long as it's consistent with KCL.
The question is, can you randomly assign the positive and negative on the resistance as long as it's consistent with KCL? Yes. So this was kind of the example I drew maybe back on the first page, right? If you have just, literally just two resistors like this, and I define positive and negative like that for both of them, all right, then in this case I know I'm going to get I1 equals I2. They have to be, right? Because there's only two things connected to that node. If you flip a coin and define them like this, right, and say, okay, by my sign convention I have I1 flowing like that and I2 flowing like that, well, I know both of these can't be positive numbers because I can't just have current, but the node is not a source or a sink, right? Current can't be disappearing there. So here, if you, whatever's connected to the rest of the circuit, one of those is going to wind up being a negative number, which means that current is just actually flowing the other way from what you initially defined, which is no different than saying I have my positive x and y axes and I have a mass moving that way with velocity v, but if you solve the problem and get a negative number for velocity, it just means it's moving to the left instead.
If this works, in the case of the differentiator, wouldn't that answer be can also work for positive?
And so you're asking if we did that for the differentiator, if you would wind up getting a positive answer here? No, so I would have to work out the full example with one of these flipped, but eventually you should get two negative signs that then cancel out and you still get the same answer. So you should always, I would have to sit, I'm not gonna have time to do it now, but you could try it. You could try exactly what I just did. Put plus there, minus there, do all the math, and you should still get the same answer. Okay? Okay. Other questions on anything so far? Current to voltage, differential, summing amplifier, or any of the stuff from earlier? I saw your hand first.
So in like, not the two recent circuits, but other circuits we have like RL, and you mentioned that that's usually like the resistance from like your measuring device.
Yes.
Do you ever have like an actual like device there, like something that they just always want like to have like a steady voltage, or is it always just like that's what you're measuring? Like, would you ever have something other than a measuring device in place of like RL?
Okay, so the question was what would you actually drive with an op amp, basically? Something other than a measuring device. That gets more into kind of, if we actually went and took a full-blown circuits course instead of this mechatronics class. Op amps, we're going to talk about transistors in a few lectures, and for purposes of this course, we use, to control something like a motor, right, we use a transistor and not an op amp. Okay, so, and that starts to get into kind of the heat transfer and heat dissipation side of things. So op amps are these little integrated circuits that actually, even though we've been saying like, oh, ideally then, they can draw as much current as they want and the output voltage could be as high as you want, in practice when it comes to drawing something like a motor, that requires a lot of current and it gets hot. So the op amps are usually going to be more used in kind of signal processing and things like the EKG, as opposed to driving mechanical loads like motors, which is, as we're going to see in one or two lectures, there are these big transistors that you can actually bolt a heat sink onto, so like there's a lot of current flowing through the motor. The transistor's better for that. So for what we're going to see in this class, hey guys, it's not quite, I got 1 minute, give me a minute, thank you. Because I wanted to try and answer, we had one more question up here real quick, and then we're good. Did you have another question?
Yeah, so for Rn and Vn for the summing amplifiers, I'm referring to the voltage and resistance for each of the sub-branch that's coming.
Yes, so that's V sub n, not V, yeah, Rn and Vn are each of, so for little n equals 1 to big N, that's 1, 2, 3, and so on. Okay? Okay, now we're good. We will get to the, if you're getting an early start on homework, whichever one is due this Friday, there is a video about active high and low pass filters on Canvas if you want to get started. If not, we'll do that in lecture on Wednesday.